Hello friends, myself Dr. Kadam Madhav, Head and Professor of Civil Engineering Department, NDMPS, KBT College of Engineering. Today we are going to discuss about the design of isolated trapezoidal footing. So for this, while you are designing the footing, the depth of foundation plays very important role. The depth of foundation is measured from the ground level to the bottom surface of lean concrete. A lean concrete of grade M15 from the thickness 100 mm to 150 mm may be provided to level the surface on the soil. The depth of foundation depends upon the nature of soil. The depth of foundation is calculated by using the formula, that is H is equal to P divided by W in the bracket 1 minus sin phi divided by 1 plus sin phi, whereas H is the depth in meter below the ground level. W is the unit weight of soil in kilonewton per meter cube, and phi is the angle of repose, and P. Design of isolated footing. The footing for an axial loaded column of size small b into capital D is designed as an inverted cantilever outstanding from the column and loaded with uniform upward soil pressure. The various steps involved in the design are given below. Proportioning of base size. Area of the footing is equal to 1.1 times P divided by FB, that is equal to LF into BF. Once the area of the footing is known, the size of footing get fixed. The shape of the footing may be square or rectangular or a circular. The size of the rectangular base is selected such that the cantilever projections of the footing from the face of the column are equal. This gives approximately the same depth for bending about x and y axis. The length or breadth of the footing based on the equal projection is obtained as follows, that is cantilever projection of the footing for bending about x axis, that is Cx, is equal to, that is LF minus D divided by 2. The cantilever projection of footing for bending about y-axis is expressed as BF minus B divided by 2, where this capital D is the depth of the column and B is the width of the column. For if the footing is designed for equal projection, then it is expressed as, that is LF by D divided by 2 is equal to BF minus B divided by 2, or that BF is equal to LF minus D plus B. Substituting the values of BF in equation 1 and solving the quadratic equation in LF, we get LF is equal to, that is D minus B divided by 2 plus under root D minus B by 2 bracket square plus AF. Here AF is the area of the footing. Select the length of the footing by rounding out the value of LF. So you will get the value of LF, and substituting this LF in this equation, we will recalculate the Cx by using calculated LF minus D divided by 2, as well as Cy, that is calculated BF minus B divided by 2, where breadth of the footing is equal to B plus 2 times Cx, where Cx is the cantilever projection of the footing, where LF and BF are the length and breadth of the footing. For square footing, LF is equal to BF under root AF. What may be the calculated area of the footing, you take the square root of, you will get the length is equal to breadth of the footing. Then area of the footing provided is equal to LF into BF. Upward, then you calculate the upward soil pressure which is acting on the foundation, that is W is equal to PU into divided by AF, where PU is the load factor into axial load, that is 1.5 times P. Then depth of the footing from bending moment consideration. The maximum bending moment is calculated as the face of the column or pedestal by passing through the section a vertical plane which extends completely across the footing and computing the moment force acting over the center area of the footing on one side of the said plane. Then bending moment at the column face parallel to the x-axis is equal to MEX, and it is calculated upward soil pressure into breadth of the footing into cantilever projection square, that is CX divided by 2. Similarly, bending moment at the column face parallel to the axis, that is MY, is equal to WU into LF into CY square divided by 2. Then required effective depth for bending moment about the x-axis is calculated about as follows, that is dx is equal to under root MUX divided by RU max into B. Then required effective depth for the bending moment about the y-axis is equal to dy is equal to MUY divided by RU max into D1, where B1 is equal to here this B1 is equal to B plus twice E is the projection provided above the footing or below the column, and D1 is equal to D plus twice E, where B is equal to width of the column and D is the depth of the column. E is offset provided at the top of the footing for sitting column formwork. While you are designing the footing, here check for shear is very important. So here check of depth footing for two-way shear. Here B of the B be the width of the column, is the offset provided for the footing. Then dy dash is equal to dy dash is the effective cover provided for the reinforcement along the x direction. Df is the depth of the rectangular portion of the footing, and df is the total depth of the foundation. Here, while you are taking a check for two-way shear, this is the column, then you could the footing will fail in a critical section at a distance of dy by 2 on both the side, where B and D be the dimensions of the column. Then you mark the critical section along the periphery of the column, that is B plus dy and D plus capital D plus dy, where BF and LF be the dimensions of the footing. A column supported by the footing slab tend to punch through the slab because of the shear stress which acts in the footing around the perimeter of the column. If the fracture occurs, it takes the form of truncated pyramid as shown. The test result indicate that the critical section can be taken at a distance of d by 2 from the face of the column. Since the effective depth dy is less than the effective depth dx, the critical section is taken at a distance of dy by 2 from the periphery of the column, where dy is the effective depth for upper layer of steel about bending about y-axis, d dash y effective cover for upper layer of steel for bending about y-axis, dx the depth for lower layer of steel for bending about the x-axis, and d dash x is the effective cover for lower layer of steel for bending about the x-axis. Then perimeter at the critical section is given by the formula, that is 2 in the bracket b plus dy plus d plus dy. By solving this above equation, we get the perimeter of the critical section is equal to 2 times in the bracket b plus d plus 2 times dy. Effective depth at the peripheral section is calculated as follows, that is d2 is equal to df minus y2 minus d dash, where y2 is equal to dy by 2 minus e into y1 divided by x1, and which is equal to df minus df minimum. x1 is equal to, that is cx minus e. Area resisting two-way shear is considered as A2, which is equal to perimeter into effective depth at the section, and which is equal to, that is 2 times in the bracket b plus df plus 2 times dy into d2. Shear resisted by the concrete, that is VC2 is equal to tau UC2 into A2, where tau UC2 is equal to Ks into tau dash UC, and Ks is expressed as this Ks, that is 0.5 times b divided by capital D, that is the cross section small dimension of the column divided by the larger dimension of the column, should not greater than 1. Then tau dash UC is equal to 0.25 times in the bracket FCK, where FCK is the characteristic strength of the concrete which is used for the footing. Design of shear to which the column is subjected, that is VUD2 is equal to W in the bracket LF into BF, that is a cross sectional dimension of the footing minus larger dimension of the column plus effective depth along the y direction into smaller dimension of the column, that is B plus effective depth along the y direction. If VUC2 is greater than VUD2, then the section is safe. Otherwise, reverse the section, that the minimum thickness of the footing at the edge shall not be less than 150 mm. The area of steel and check for development length. Required area of steel for bending about x-axis is expressed by the formula, that is AST x is equal to 0.5 times FCK divided by F in the bracket 1 minus under root 1 minus 4.62 MUX divided by FCK B1 into dx square divided bracket close b into dx. It should not be greater than AST minimum, that AST minimum and AST minimum along the x direction and AST minimum along the y direction is expressed discussed in the next slide. Required area of steel for bending moment about x-axis is the same formula, only here changed is the moment about the y-axis and the capital D and dy, where in the above formula B1 is the B plus 2 times E and D1 is equal to D plus 2 times E, where B is the smaller dimension of the column and capital D be the larger dimension of the column and E be the offset for the column. Then AST minimum is expressed as 0.85 times B1 into dx divided by Fy. Similarly, ASTY minimum is expressed 0.85 times D1 into dy divided by Fy. As the footing is designed as a wide beam, minimum reinforcement as specified above shall be provided. In rectangular footing, the reinforcement parallel to the long direction shall be distributed uniformly across the width of the footing. The shorter direction since the support provided to the footing by the column is concentrated near the middle, the moment per unit length is largest. That is, the curvature of the footing is sharpest immediately under the column and decreases with the measuring distance from the column. For this reason, larger steel area is needed in the central band in the shorter direction and is determined in accordance with the equations given below. That is, reinforcement in central bandwidth into BF divided by total reinforcement provided in along the y direction in the shorter direction is equal to 2 divided by length of the footing divided by breadth of the footing plus 1. The remainder of the reinforcement shall be uniformly distributed in the outer portion of the footing. The remainder of the reinforcement shall be uniformly distributed in the outer portion of the footing. Then required development length for bending about the x-axis is given by LDX, that is equal to 0.87 times Fy divided by 4 times tau BD into phi x is the diameter of bar used for the footing. LD available is equal to Cx. Required development length for bending moment about the y-axis is equal to LDY is equal to 0.87 times Fy divided by 4 times tau BD into phi y, that is the diameter of bar provided along the y direction, and LD available in this case as a Cy. Cx and Cy be the cantilever projection of the footing which is measured from the face of the column, where phi x and phi y are the diameters of the bar for bending about x-axis and y-axis respectively. LD available should be greater than LD required. LD is equal to AST required divided by into LD. Before discussing about this development length, I want to tell you about something about the footing before checking for the development length. The check for development length may becomes critical in the case of soil having larger bearing capacity. In that case, the size of the footing required works out to be small, resulting in lesser cantilever projection. If the development length increased is not satisfied, it can be made to satisfy by 3 alternative methods, that is, decrease the bar diameter, increase the width or length of the footing such that the projection of the footing from the face of the column, that is Cx and Cy, is not less than the required development length plus cover. Provide 90-degree bend at the edge of the footing. Increase the area of the steel so that the stress in bar will get reduced, and the modified development length LD is approximately given by, that is LD modified is equal to AST required divided by AST provided into LD. Shear for bending about a y-axis is normally critical. The check for one-way shear is carried out on the same line in the case of beam. Critical section for one-way shear about y-axis is taken at a distance of dy from the face of the column for the cantilever portion of the footing. For bending about y-axis is less than the depth of the footing. One-way shear check is not necessary. The check for one-way shear can be carried out using the following steps. These are the check for one-way shear can be carried out using the following steps. That is, first of all, you calculate the d1. d1 is expressed as a y1 minus in the bracket dy minus e into y1 divided by x1, where y1 is expressed as a df minus df minimum and x1 is equal to cy minus e, where cy is a cantilever projection along the y direction and e is the offset provided for the footing. Width of the footing at critical section is expressed as a b2 is equal to d plus 2 times dy. Area of the footing at critical section is equal to trapezoidal area plus rectangular area. So area along the y direction is equal to, or it is calculated b2 plus lf into d1 divided by 2 plus df minimum minus dy dash into lf, where dy is equal to effective cover for bars at the top, that is d dash x plus 5y. Percentage of steel is expressed as 100 into ASTY divided by AY. Then design of shear is calculated from the table 19 of IS 456/2000. Shear registered by the concrete is VUCY is equal to tau UC into AY. This tau UC is calculated from the IS code. Shear to which the column is subjected is equal to that VU dy, that is ultimate upward soil pressure into LF into CY into dy. If VUCY is greater than VU dy, then section is safe. If VUCY is less than VU dy, the section is unsafe. Then either increase the steel or change the section of the footing and process, and the process is completed. Check for one-way shear for bending about the x-axis. Here instead of y it will be x. The critical section is taken at a distance of dx from the column face. Cx is less than dx. One-way shear is not required. The procedure for carrying out the check is similar to the one given before. Depth of the footing above the rectangular portion is expressed as a d3 is equal to y1 minus dx minus e into y1 upon x1, where y1 is equal to df minus df minimum and x1 is equal to cx minus e, where cx is a cantilever projection along the x direction and eb is the offset provided for the footing. Width of the footing at critical section is expressed as a b3 is equal to b plus 2 times dx. Area of the footing at a critical section is equal to trapezoidal area into the rectangular area, that is ax is equal to b3 into bf into d3 divided by 2 plus df minimum minus d dash x into df. Percentage of steel is expressed 100 into ASTX divided by ax. Design of shear stress, which is calculated from the table number 19 of IS 456/2000. Shear registered by the concrete VUC is equal to tau UCX into X. Shear to which column is subjected, that is VU dx is equal to W into BF CX into dx. If VU CX is greater than VU dx, the section is safe. If VU CY is less than VU dy, the section is unsafe. Then either increase the steel or change the section of the footing as and process is repeated. Though check for one-way shear along the x direction and along the y direction, the approximately steps are same. Check for bearing pressure at the column base. This is the last step in the design of footing. When the column rests on the footing, it transfers its load only to the part area of the footing. The adjacent concrete of the footing provided lateral support to the directly loaded part of concrete. This causes increase in the strength of the concrete which loaded directly under the column. This effect is taken into account and the code provides that the compressive stress in concrete at the base of the column or pedestal shall be considered as being transferred by bearing the top of the supporting pedestal or footing. Based on this code provides that actual bearing stress on the loaded area should be less than permissible bearing stress into under root A1 upon A2, that is PU divided by cross-sectional dimension of the column. It should be less than 0.45 times FCK in the bracket under root A1 divided by A2, and A1 and A2 should not be greater than 2, where A1 is calculated LF into BF or B plus 4 times DF into D plus 4 times DM, whichever is less, or it, and A2 is the loaded area of the column base, that is expressed as a B into D.